Ever wondered how a prism can split white light into a rainbow of colors? Or why a straw seems to bend when you dip it in a glass of water? The answer lies in refractometry. This fascinating field of physics explores the bending of light as it passes from one medium to another. We'll unravel the mysteries of refractive index, specific and molar refraction, and learn how to measure this bending of light using various types of refractometers. Ready to dive into the world of light and refraction? Buckle up! First off, let's decode the refractive index, the heart of refractometry. Now imagine a beam of light racing through space. It's moving at its top speed, the cosmic speed limit, the speed of light in a vacuum. But what happens when this light hits a medium like water or glass? It slows down. This slowdown is not random and is quantified by a value called the refractive index. The refractive index, denoted by the letter N, is a dimensionless number that describes how light propagates through a particular medium. It's defined as the ratio of the speed of light in a vacuum to the speed of light in the medium. So if light travels slower in a medium, the medium's refractive index is higher. But why does light slow down? Well, it has to do with the medium's optical density. Optical density is a measure of how much a medium slows down light waves. The denser the medium, the slower light travels, and the higher the refractive index. For instance, diamond, which is optically denser than water, has a higher refractive index. Now, you might be wondering, how does the refractive index affect our everyday life? Well, every time light enters a new medium, it changes direction, a phenomenon we call refraction. The extent of this change in direction is directly related to the refractive index. This is why a straw appears bent in a glass of water, or why distant objects shimmer on a hot day. The refractive index is behind all these optical illusions, but the refractive index is not just about optical illusions. It's also crucial in technologies like lenses, fiber optics, and even in determining the purity and concentration of substances in industries like pharmaceuticals and food processing. So, the refractive index is not just a number, but a telling sign of how light interacts with different mediums. It's a fundamental concept in physics and an essential tool in many scientific and industrial applications. By understanding the refractive index, we can begin to comprehend the subtle and intricate dance of light in our universe. Now that we have the refractive index down, let's explore specific and molar refraction. Specific refraction, sometimes called the refractivity, is a measure that relates the speed of light in a medium to the speed of light in a vacuum. It's essentially the refractive index, but with a little twist. It's adjusted for the density of the medium. So when light passes through substances of different densities, we can use specific refraction to compare how the light behaves in each. Now on to molar refraction. This is another way to express how light behaves when it moves through different media. But this time, it's all about the number of molecules. Molar refraction takes into account not just the speed of light in the medium compared to a vacuum, but also the volume occupied by 1 mole of the substance. It's like getting a glimpse into the molecular world, understanding how the very building blocks of a substance affect the way light travels through it. So, how do specific and molar refraction relate to the refractive index and the composition of the medium? Well, they're all interconnected. The refractive index gives us a general idea of how much light is bent or slowed down when it enters a medium. But specific and molar refraction give us a more detailed view. They allow us to see how the density and molecular structure of the medium affect its interaction with light. Think of it this way. If the refractive index is like knowing the average speed of cars on a highway, then specific refraction is like knowing the speed of each individual car, and molar refraction is like understanding how the design and build of each car affects its speed. With specific and molar refraction, we can delve deeper into the characteristics of the medium the light is passing through. We're not just looking at how much the light bends, but also why it bends the way it does. And that opens up a whole new world of understanding about the nature of light and matter. Knowing the refractive index is great, but how do we measure it, you may ask? Well, we use the very thing that gets refracted, light. So let's dive into the world of light and refraction. Imagine a beam of light hitting a boundary between two mediums. Some of it gets reflected, but some of it enters the second medium. This light, however, doesn't continue in a straight line. It changes direction or refracts. The angle at which it refracts depends on the nature of the two mediums. Now, what's the connection to refractive index? Here's where a nifty little law comes into play, known as Snell's law. Named after the Dutch astronomer Willebrord Snellius, it provides us with a mathematical relationship between the angles of incidence and refraction and the refractive indices of the two mediums. It's essentially a ratio that tells us how much the light will bend. To measure the refractive index, we measure the angle of incidence and the angle of refraction when light passes from one transparent medium to another. Using these angles and Snell's law, we can calculate the refractive index. So by harnessing the power of light and using some simple mathematics, we can unlock a world of knowledge about the materials we're studying. And that's how we measure the refractive index, using light itself as our guide. To measure the refractive index, we use tools called refractometers. Let's get to know them. These instruments, as varied as they come, share a common purpose: to determine the refractive index of a substance. They do this by measuring the degree of light bending or refraction when it passes through that substance. First in our list is Abbe's refractometer, named after the German physicist Ernst Abbe. This device is the classic model, widely used in laboratories. It operates on the principle of critical angle, a concept that when light hits a boundary between two substances, there's a specific angle at which it will be completely reflected back into the original substance. Abbe's refractometer measures this angle and uses it to calculate the refractive index. Next, we have the dipping or immersion refractometer. This one's pretty straightforward. As the name suggests, it involves dipping a prism into the substance under examination. The refractive index is then determined by the angle at which light is refracted as it passes through the substance and the prism. Then there's the Pulfric refractometer, a type of differential refractometer. This device employs two prisms, one filled with the substance being tested and the other with a reference substance. By comparing the refraction of light in both, we can deduce the refractive index of the test substance. Finally, we come to the image displacement refractometer. This one's a bit more complicated, but bear with me. It involves two prisms and a light source. The light is refracted twice, once in each prism. The refractive index is then calculated by measuring the displacement of the refracted light's image. From simple to complex, these refractometers help us unveil the secrets of light. Each has its own unique way of interacting with light and substances, revealing the fascinating world of refraction. Understanding them not only broadens our knowledge of refractometry, but also deepens our appreciation for the intricate dance between light and matter. So, where do we use refractometry in real life? Let's start with the medical field. Refractometry is used to measure the protein levels in bodily fluids, which can help diagnose a variety of conditions. Think of it like a detective helping to solve the mystery of what's happening inside our bodies. Next, consider the food industry. Here, refractometry measures the concentration of sugar in fruit juices or the alcohol content in wines and beers. It's like the quality control expert, ensuring that your favorite beverages taste just right every single time. In the realm of geology, refractometry assists in identifying minerals. Each mineral has a unique refractive index. It's as if they each have their own fingerprint. This is a crucial tool for geologists as they explore the wonders of our planet. And let's not forget about the petrochemical industry. Here, refractometry determines the quality of oils and fuels. It's the silent guardian that ensures your car runs smoothly and efficiently. But wait, there's more. Refractometry also plays a role in the pharmaceutical industry, where it's used to determine the concentration of drugs. It's the unseen hero, ensuring that medications are safe and effective. And finally, in the world of optical fibers, refractometry is used to measure light transmission. It's the conductor, ensuring that data travels quickly and accurately, keeping us connected in this digital age. From our kitchens to hospitals, refractometry shines its light everywhere. And that's a wrap on our refractometry journey. We've delved into the intriguing world of refractive index, specific and molar refraction, and how to measure these using the angle of refraction. We've also explored the various instruments involved, including Abbe's dipping, immersion, Pulfric, and image displacement refractometers. Finally, we've seen the vast applications of refractometry in different fields. Subscribe for more because you won't find me later. Keep exploring, keep learning,